All right, everybody, welcome to the video here for the practice questions for lessons 9 and 10. So I just put together a couple questions here just to make sure that you totally understand the concepts for lessons 9 and 10. Hopefully in class you worked with somebody that was either able to help you out or maybe you were able to help them out. All right, but these questions kind of just become repetitive over the course of the last few lessons. So again, it's just a day to make sure that everything that you knew or didn't know is all cleaned up here before moving forward to new stuff in lesson 11. So number one says Kelsey places a $3,200 investment in an account earning nominal interest rate of 4.8% compounded continuously. So it says write a function for K of T, the amount of money Kelsey has in the account after T years. So as soon as I see that word continuously, I know we're talking about the PERT formula. So we're going to say the Kelsey function is equal to the initial amount, 3,200, e to the 0.048 t. So remember the PERT formula is, whatever the future amount is PE to the RT. Then I want us to figure out, well, how much money does she have in the account after 12 years? So that would be the value of K of 12. And I would just plug that right into my calculator. Remember, E is just a button on your calculator. You can get it by hitting second and then LN, which is over near the number 4 button. So 3,200, second LN, 0.048 times 12. And we get Kelsey has in 12 years approximately $5,692.51. The next part says to determine the effective rate for this account. So we want to change this so that the exponent is just t. So I'm going to rewrite Kelsey's equation here, but I'm going to put in the parenthesis e to the 0.048 all to the t power, just separating the decimal and the variable t. Now what happens is whatever this number is in here represents our yearly rate because the exponent is in terms of years now. So if I type just into my calculator the e to the 0.048, I can rewrite Kelsey's equation as $3,200 times 1.0492 all to the t. And this, remember, represents 1 plus r since it's more than 1. So the rate is going to be that number minus 1, so that would be 0.0492. Or about 4.92%. Notice the effective rate is a little bit more than the nominal rate because the effective rate takes into consideration that your interest is also compounding on itself. Number 2, Ava's investing $620 in an account with a nominal rate of 8.4% that compounds continually. Again, that word continually, so we need the PERT formula again. So it says write a future value account for t years. So we have f of t is equal to $620 e to the 0.084 t. How much money does she have in 8 years? Just plugging in 8 to the formula. Again, most of this is just recognizing, well, which formula do I have to use, right? We learned a bunch of them, so we want to make sure that we use the correct one each time, all right? So again, just plugging that into our calculator here. And we get Ava has, after 8 years, $1,214.05. Whenever we're dealing with money, remember, always round out 2 decimal places. Third part here says use the graph on your calculator to approximate how many years it would take for her to triple her investment. So if I take 620 and times by 3, that's 1860. So I want to know when is 1860 equal to 620 e to the 0.048 t. So this is something we've been doing since like the 5th lesson of the chapter. So I have an equation that I can't solve algebraically, but I can solve graphically by setting both sides of the equation as an equation in my calculator and then see where they intersect. You're going to get a straight line equation for the 1860, and you're going to get an exponential growth function for the other side. I want to know where they intersect, right? So I see that after 8 years, I get to like $1,200. So I'm going to assume if I go out like 15 years on my x-axis, that's probably good enough. And I want to make it so that my y-axis gets me at least to 1860. So I'll make my y window go up to 2000. So go into your y equals and graph this. So when you're graphing these, again, you're just thinking, what is a logical window? What's a window that makes sense, right? If you're wrong by guessing the window, you can always change it. That's the beauty of it. So I'm going to make my window 0 to 15 and 0 to 2000. And 15 wasn't enough. So bad guess. So go back in the window. Try a different number, like try 20 or 25 or something like that, right? I tried 25 and 25 worked. So then hit second trace, go down to intersect, enter 3 times, and we get an intersection of 22.8877, comma 1860, which means it's going to take her to nearest tenth of a year, 22.9 years. The next part of this asks you to determine the effective rate of the equation. So just like we did with the Kelsey equation above, I want to rewrite it so that it's in terms of an exponent that just represents years. It doesn't represent anything multiplied to the years. So then if I plug that into our calculator, so if I go e to the 0.048, I get f of t, which is equal to 620 times 1.04917 all to the t. And remember, this is 1 plus r, so subtract 1. So my rate is 0.0492 or 4.92%. I wrote that backwards. Shoot. That was 84, not 48. My bad. Let me just pause this for a second. I'll clean this up for you. All right, welcome back. Sorry about that. So I had it graphed wrong because I had 48 instead of 84, but I changed it, updated it here. So our intersection was around 13.1 years. And when I redid my rate here using the correct decimal, I got 1.0876. Hopefully these are the numbers you got. So subtract 1, just like I was saying before, and here we get 8.76% as the effective rate. Okay, on to half-lives, right? So something that we noticed about half-lives is we always have kind of like the same equation. It's always the initial times a half, all to the time over the amount of time it takes to make a half-life. So AU-195 is a type of gold that actually decays in 186 days. It's kind of like a isotope. We have this half-life happening in 186 days, and we're starting with 400 grams. So we could say G of T is equal to 400 grams times 1/2, all to the T divided by 186 for the number of days it takes. Only thing we really have to be careful of here is to make sure that the half-life and the model matches in the terms of time. Next says, what percentage is remaining after 365 days? So days, so that's your T. So I can say G of 365, so a year. I start with 400 grams. We have 1/2 to the 365 over 186. Type that in our calculator. And we get, after 365 days, we get 102.64 grams. Now, that's not what they're asking. It's not asking how many grams are left in 365 days. It's what percentage, right? So it says what percentage is remaining after 365 days. So I can figure out, well, the original amount is 400. If I divide 102.64 and 100, I get 0.2566. Now that's the percentage that's left. So if I multiply that to a percent, there's about 25.66% left. Then it says use properties exponents to change a model in terms of a yearly rate. So instead of this being a half-life rate going 186 days, if I rewrite this so that the exponent is just t, and I'm going to change this to 0.5, just makes my life easier in a calculator, all right? We multiply it so that just t is the exponent. Now it's in terms of the yearly rate, kind of like what we did in the previous lesson when we were talking about effective versus nominal interest rate. So if we do 0.5 to the exponent of 1 divided by 186, we can say g of t is equal to 400 times 0.9963 all to the t. So that's the equation in terms of the yearly rate. I could even find the yearly rate by figuring out what 1 minus that number is. So if I do 1 minus that number, I get, around 0.37%. Small percentage. Number 4 talks about Newton's law of cooling. Newton's law of cooling is just a fancy formula that's used to determine how long it takes something to go down in temperature. We can also use Newton's law of cooling to see something rise in temperature, but for the most part, it's the law of cooling, so it's going to go down. So there are a bunch of variables in the law of cooling here. So we have an ambient temperature, the temperature of the surrounding, the initial temperature, T sub 0. Science people, you'll notice sub 0 in science usually means initial value. K, so the constant of cooling. So every object has a kind of like a ratio that shows how long it takes to cool. And then T is the time in hours it takes for something to cool. So here's a little word problem here that I made up about one of our fellow math teachers, Miss Perry. So it says every day at 10 a.m., Mrs. Perry microwaves herself a lean cuisine, and she wants to eat that for lunch. When a meal comes out of the microwave, it has a temperature of 88 degrees Fahrenheit. That's the initial temperature. That's T sub 0. Then it says on Monday, she made herself her meal and placed it on her desk in her classroom, which is always 70 degrees. That's the ambient temperature. That's the surrounding temperature, T sub A. It then says, well, unfortunately, she had some kids come in for extra help and she forgot to eat her lunch. So essentially, her lunch is sitting on her desk from 10 a.m. until 2 p.m. So from 10 a.m. to 2 p.m., that's a total of 4 hours. So we have almost everything we need to be able to determine the temperature of Miss Perry's lean cuisine after that 4 hours of sitting on her desk. And the only missing piece was knowing the constant of cooling. So the constant of cooling for her lean cuisine is 0.235. Don't ask me how I figured that out. We did some math, right? So to figure that out, we can now plug in everything. So after 4 hours, we can say the ambient temperature of 70 degrees plus the difference between the initial temperature and the ambient temperature, E, to the negative 0.235 times 4. Now this just becomes a can I plug it into my calculator question, right? So just be careful if you have to do it part by part. So I have 70 plus 88 minus 70. You do all that quick math, 0.235 times 4. Notice I left the constant as a negative value. It's in the formula as a negative value, so we want to keep it negative. Unless the constant of cooling is negative, then it becomes a double negative. But we'll notice if we plug it in wrong, the temperature will actually rise, which wouldn't make sense here because the temperature should go down. And it says round to nearest hundredth, so 03 degrees, 77.03. Right? Which makes sense, because if I take something hotter than room temperature and leave it in room temperature, it's going to cool down towards room temperature. Then it says, estimate the time of day on Monday to the nearest hour it would take for the temperature of the lean cuisine to reach 72 degrees. Explain how you arrived at your answer. So if I take 72 and set it equal to the ambient temperature plus x minus 70's ambient temperature. So, 88, my bad. E to negative 0.235 x. Just like we did, we have two equations here. I have a y sub 1, and I have a crazy looking y sub 2. But what's going to happen is when I graph this, I'm going to have a value that comes across, that's the 72. And I'm going to have a temperature that starts up high and is going to come down like this. So what we need to figure out is where do they intersect? And then how long does that take? Because that would be my x value. So if we graph both of those, we can figure out where that is going to kind of intersect. I'm just going to pause the video here so I can type. All right, so now that I have everything graphed, I want to change up my window here. So for my window, I know that the maximum temperature is going to be 88 degrees. It's not going to get hotter than that. That's the hottest it is coming out of the microwave. So I made my max temperature a little bit more than that, so 90. My minimum temperature I also kind of know. So since Miss Perry's classroom doesn't ever go below 70 degrees Fahrenheit, neither is her lean cuisine. Even if it sat there for a month, it wouldn't go below that temperature. So I made my Y min a little bit below that, so I made it 60. And to figure out the X value, you're literally guessing. You're saying, how long can I estimate that this is going to take to happen? So I think it's going to take about, I don't know, 15 hours or so. So I'll go out to 15 on my x-axis. And then when I do that, I see that I was kind of over guessing because it comes out to be about 9 hours. So in finding the intersect button here, we got 9.3 hours, comma 72. So that takes about 9.3 hours to happen. So it says to the nearest hour, right? So estimate the time of the day on Monday to the nearest hour it would take for the temperature to reach 72 degrees Fahrenheit. So since it takes about 9 hours, so if I start at 10 a.m. and I go 9 hours, it's going to be approximately 7 p.m. when it reaches that temperature. Actually, it would be a little bit more because of the 0.3, but it says to round, so we'll just round to nearest hour. Hopefully this video helped. Hopefully you were able to get some practice in either today in class or tonight for homework. I'm not sure how this was assigned to you. And good luck. I will see you all soon.